All right, next I want to look at another two-body problem that involves friction. Here we have a 4 kilogram mass on a horizontal surface with a coefficient of kinetic friction and a hanging mass. So this is a little bit like the Atwood machine problem and a little bit like one of the friction problems that we've been looking at combined together. And so what we want to do in these kind of problems is to first draw a free body vector diagram for each mass. And so this is critical to being able to work the system through to its completion. Here we know that the hanging mass is going to overwhelm the 4 kilogram mass provided the object is already in motion. And so that means that the 7 kilogram mass will be moving down. We'll call that the positive direction. And then it has forces acting on it due to gravity, m2g acting down, and a tension force acting up, such that for m2, we can say that, with this being the positive direction, m2g minus t equals m2a. Remember that m2a is the sum of the forces, and that's equal to the mass times the acceleration. Okay, so the sum of the forces here equals ma. For m1, do the same thing. Now here we've got vertical and horizontal forces. So in the down direction we've got m1g, the upward direction we've got F normal. So for F1, or m1, we can say that the sum of the y forces is 0, or that F normal minus m1g equals 0. And that gives us kind of a standard result for our normal force, which can be plugged in to the friction force for the horizontal problem. Okay, so for the horizontal problem, I'm going to redraw this down here, just the m1 part. And so there's going to be a tension pulling this way, and there's going to be a force of friction slowing it down. So that we can say that T minus force of friction equals m1a, or T minus mu k times the normal force. Okay, but the normal force is m1g from the top equation, so we write this as mu k m1g equals m1a. And again, we've chosen the positive direction to be down for mass 2, but to the right, the positive direction for x at least, is going to be to the right for m1. So for m1, our relevant equation is going to be tension force minus mu k m1g equals m1a. Now we can take this expression and we can add the two equations together, and that eliminates the coupling tension. And this is something we can always do, is just add the equations together, and the coupling force will cancel out. Okay, so this is our free body diagram for m1, and I expanded this part of it out, the x part of it out, so that the sum of the x forces here equals m1a. Okay, so here we can say that m2g minus mu k m1g equals m1a plus m2a, or m2 minus mu k m1 times g, m1 plus m2 times a. And finally we get here a is equal to m2 minus mu k m1 divided by the sum of the masses, all times the acceleration due to gravity. Okay, so here we have taken and written equations using Newton's second law for each mass, and then here, using algebra, we've solved those equations simultaneously. So that now we can plug in numbers, with M2 being 7. Write this then as 7 kilograms minus 0.5 times 4 kilograms divided by 7 kilograms plus 4 kilograms, all multiplied by g, which is 10 meters per second squared. Okay, so that's 7 minus 2 is 5 over 11 times 10. So that gives us 7. One more time. It gives us 4.54 meters per second squared. Okay, so that's our acceleration for this problem. If we wanted to, we could go back and get the tension, which is the same here in this part of the chord as it is in that part of the chord by Newton's third law. The force of M2 on M1 equals the negative of the force of M1 on M2. So that's just Newton's third law acting. And then remember that the tension forces are always pointed away from the mass in the direction of the string. Okay, so next, what I'd like to do is take a look at a problem that involves a mass being pushed on as it goes up an inclined plane. So in this next example, say we have a mass here, m, set m equal to, say, 10 kilograms. Let's make this angle here 30 degrees. Let's say we have a force that's acting horizontal. And let's say that's equal to 100 newtons, acting horizontally to the system. And so from this, with a mass of 10 kilograms, let's find if there's some friction on the surface, say mu k equals 0.5 again. Let's find the acceleration of the mass up the incline. Now, if you remember from our strategies before with inclined planes, is we really do want to use the coordinate system that is parallel to and perpendicular to the incline. And so this is going to be my xy coordinate system. And that means that my force, F, is not in that direction. And neither is mg here. But the normal force is. So the normal force is in the positive y direction. But both the horizontal and the vertical forces here of mg and the applied force are not. And so therefore, they're going to have to be converted into components of the force that are in this direction. Okay, so we've already learned how to do this with mg. Remember that if we draw a vector triangle here, this adjacent side is mg cosine of theta, where this theta is the same as the theta for the inclination of the incline. So again, that's something that you should commit to memory rather than trying to derive that every time. And then this force here is mg sine 30. So we can also think of that as acting right through the mass, which is helpful here. That's mg sine 30. Now, we should try to see whether or not this force has a component up the incline that's greater than mg sine 30. Otherwise, if this mass is in motion, it might be decelerating. Okay? And so what we would want to do here for this force is to break it up into x and y components. And so the x component would look like this, and the y component would be negative and would look like that. And so that tells me that the normal force is going to have to be bigger than it would usually be, because it has to withstand the crushing force of this horizontal force that has a vertical component which tends to smash it into the incline. Okay, now, because this line is parallel to that line and this line is parallel to that line, you can immediately say that this angle here is 30 degrees. And so therefore, this x component is f cosine 30, and this y component is f sine 30. So we've got that, and then finally, we can see, well, f cosine 30, that's going to be 100 times the square root of 3 over 2. So that's bigger than mg sine 30. mg is 100, because m is 10, g is 10, so that's 100. Sine of 30 is 1/2, so 50 is going this way. 86.6, which is f cosine theta, is going that way. So the f cosine theta is winning, and that means that the mass will accelerate with a positive value up the incline. Okay, and so if we were to look at an inclined plane, like this one here, and I were pushing with some, this would tend to slide on its own, but because I'm pushing horizontally, I'm pushing hard enough to make this thing go up the incline with an acceleration. All right, so what we have then is a slightly more complicated x and y equation. We can say that the sum of the y forces is 0, because the mass is moving along the incline and is not accelerating or moving with any velocity up, away from the incline. It's not being crushed into the incline because the incline is not collapsing. So here we can say that F normal, that's a vertical y force, mg cosine of 30 is a negative force because it's in the negative y direction, and F sine 30 is also in the negative direction. So that's going to equal 0. This gives us an expression for the normal force. Now, why do we need that? Well, we wouldn't have needed that if there weren't friction. But there is. Here's our friction force. F friction. That completes the vector diagram. Now we've got friction force mg sine 30 in the negative direction, and F cosine 30 in the positive. And so the friction force depends on the normal force. And so that's why we need the normal force, is to get the friction force. So this would be F sine 30 plus mg cosine 30. So that's our normal force. And so now our sum of the x forces is equal to mass times acceleration. Okay, so our x forces then are going to be F cosine 30 minus mg sine 30 minus the coefficient of kinetic friction times the normal force, which in this case the normal force is F sine 30 plus mg cosine 30. All right, so that sum of the x forces then is equal to ma. All right, so we have now basically worked this down to one equation and one unknown. We had two unknowns because we didn't know what the normal force was. That's why we had to solve the vertical equation. The horizontal equation, we didn't know what the acceleration was. And so, but that also included the normal force. So we eliminated the normal force here in favor of known quantities. And so now we can just plug in and solve for the acceleration. So here this is going to be 100 newtons, that's F, times the cosine of 30, 0.866, where the cosine of 30 is root 3 over 2. The sine of 30 is 1/2. So this is 0.866. So this all comes from, again, our 30, 60, 90 right triangle, 1, 2, square root of 3. Okay, so here then we've got M, that's 10 kilograms, times G, 10 meters per second squared, times the sine of 30, 1/2, minus mu k, 0.5, times, and then here F sine 30, that's 100 newtons times 1/2, plus mg, which is 10 kilograms times 10 meters per second squared, times the cosine of 30, which is 0.866. That's equal to 10 kilograms times A. Okay, so I've got all the numbers, but I've also got the units in this expression. So what I'm going to do to finish this up is just drop the units. So this first term then is going to be 86.6. The second term is going to be 100 times 1/2, which is 50. This third term is going to be 1/2 times 50 plus, this is 100 times 0.866 is 86.6. It's equal to 10A. Okay, and so here, this will be, I'm ready to just punch that out. So that gives me 31.7 minus 31.7. No. And this is minus. Oh, but then we have this. Okay, so even though the tendency of this system is to go up the incline, this number here is big enough so that the acceleration itself will actually be negative. So what we end up with then is an acceleration A of minus 3.17 meters per second squared. Okay, now with a negative acceleration like this, it means that it had to already be moving, and the net force is acting to slow it down. So it eventually would come to rest as it moves up that incline, even under the influence of this constant force.